We model intricate structures using frame elements. While it is easy to imagine and depict these frame elements with some depth, they are nothing but one-dimensional mathematical constructions. This becomes more apparent when we deal with deeper frame elements. For instance, when modeling a simple structure, we can get away with just a few nodes and frames. When we try the same strategy with deeper frame sections, things start to look a bit strange, especially closer to the joints. It appears that our beam is starting to deflect long before it even exits the column, overestimating the actual length of the beam and its midspan deflection. We're also applying loads over the entire length of the beam, overestimating the actually loaded length. Not to mention, the distribution of the internal forces is not accurate at all because of this unexpected and sometimes unaccounted behavior. A smart way of handling this issue is to utilize rigid links. We can utilize these fictitious elements to create better connections. This allows us to simulate the distributed loads better, solve the problem of deflections inside the columns, and calculate more accurate internal forces. Another limitation of one-dimensional frame elements is the inability to position deeper beams of a structure flush at the floor level. Assuming the nodes are located at the floor levels, none of our beams are positioned properly here. We can use rigid links to resolve this issue as well. Sometimes our columns may not be perfectly aligned vertically. Normally, this would lead to eccentricity and additional moments in the bottom column. However, we cannot simulate this behavior without rigid links either. One last help we get from the rigid links is related to the arbitrarily angled roll supports. These are difficult to simulate with the displacement method, as our degrees of freedom are defined in fixed components of the Cartesian coordinate system. Rigid links can help us simulate these as well. Thanks to their large axial stiffness, we can use rigid links to force a restraint in any direction. For instance, this construction only allows movement orthogonal to its axial direction. We can orient it in any direction to simulate an angled roller.